Is Professor K.R. GURUPRASAD. He is an associate professor in the Department of Mechanical Engineering at IIT Kanpur. He received his M.Sc. in 1997 and Ph.D. in 2009, both from Indian Institute of Science, Bengaluru. His research focuses on control system, motion planning, multi-robot systems, and their real-world applications. Today, he will be presenting on the topic multi-robotic systems and Voronoi Partition. Please welcome Professor GURUPRASAD to the stage for his talk.
Right? Okay. Thanks to Ashwini for all the effort, and thanks to Professor Debashish Ghosh, because of whom I am here now. Okay. Listening to the Professor Viravalli, right? Talk.
Yes.
I mean, initially I thought I am not working in computation, so my talk is put in computation. I realized I do quite a bit of distributed computing indirectly, though that is not my focus. Okay. So what I am trying to do is, you can see this 61. So don't worry about this. I'm not going to talk about all the 61 slides. It's mainly my focus is on around first 20 slides. Indirectly, this gives me my academic journey, starting from my PhD with Professor Ghosh, leaving out my master's with Professor Ghoshal, which I presented when he was retiring. Okay. So my topic is multi-robotic system. That is what I was introduced during my PhD. And I happen to use a tool called Voronoi Partition, where I am still stuck. I mean, whichever problem I see of multi-robotic system, I feel that Voronoi Partition is the best possible solution. Okay, so that is what is the topic. And doesn't work. Point here? No, it should be this one, no? No, that is not very convenient. Okay, can you just... Okay, that's not connected. Okay, so this is what I'm going to talk about. And there are a few things. My focus will be on multi-robotic or UAV is a robot for me. It's an aerial robot. Research. This is what was my PhD dissertation on when while I was here, and I continue working on this through my PhD students. And this was my postdoc work. The reason I will not talk about that, I'll just show that. The reason I'm talking about that is how I continued from here to a different topic. Okay, so the Voronoi partition became some common thing, and then I'll just show in one slide other representative work. Okay, so this is let me not read out this because it will become boring. So let me actually give you this slide. This is what actually gives the problem, the primary problem that we are talking about. So you have multiple UAVs, and during my PhD I did not bother about what my agents are. They were all point masses. During my PhD student work, we thought we will have quadcopters instead of generic agents. Okay, but the problem statement doesn't change much. And with quadcopters, I don't have to worry about non-holonomic constraints and things like that. I don't get into that details. Okay, so you have a large area, and we have multiple quadcopters. For convenience, we have shown three. Three becomes multi-agent systems. Okay, and you have, these are representation of some targets of interest. In real life, targets of interest could depend on an application, what you are looking for. Okay, so as an academician, I'm interested in converting the problem into an abstract setting, and then looking at this. I have represented them as triangles here for two purposes. One is for representation, and later in our research we have actually used triangular object for doing certain experiments. So each one of them has got a downward facing camera, and they'll look at the image within certain domain and then try to detect the targets. My problem here is I want to detect all the targets available in the within. For example, if you have a natural calamity, you might want to look for survivors, and these targets are not dynamic, they are not moving, because of course that is easier, that is one thing, and there are many applications that that is the reality. Okay. So you have multiple of these things with downward facing cameras, they are looking for targets, and our interest is we want to detect all the targets. Okay. And since we are using multiple robots, how do we optimally use them in such a way that you can do it faster? Okay. So the optimal deployment is the key factor here. And in this background, let me just go here. So this is a formal definition of that, let me note. And this is a tool which is Voronoi Partition. So while I was doing PhD, I had gone to Kyiv for a conference. I had visited Voronoi's home, named after Georgy Voronoi, I suppose. I write only G. Okay. So he was something like our Srinivasa Ramanujan. I heard he died around in his 30s. And so my exposure is only this Voronoi Partition, but he has a lot of contribution like Srinivasa Ramanujan on, I think, number theory and stuff like that. Okay. So basically what is Voronoi Partition? You have some node here. This plus marks are certain nodes. It's abstract. You collect all the points which are closest to this particular node. That will become a Voronoi cell corresponding to this node. Okay. Now this is very useful because there is a natural optimality involved here. If you have a robot here, or this is also used in something called facility location. So if you have a facility here, let us say there are several service centers. If this service center, if you are here, you will go to this service center, not this. So that way there is a natural optimal partition based on Euclidean distance. So this is a tool which is very useful for me, because here there are two problems. When I initially address the problem, now I assume my sensor range is infinity, right? So if there is a point here which can be seen by all UAVs, so which one you should use? Okay? So obviously you will try to use the nearest one. Okay, there are different models possible. For example, this fellow can be seen only by this in a limited sensor range application. Okay, so initial problem formulation, we did not have limited sensor range. In principle, if I have one UAV, it can see entire space. That is a kind of theoretical assumptions we make. Even in there, what happens is, if this fellow actually, for example, there are points here, there is a point here, which can be seen by all three UAVs. Okay? So my question is, which UAV should actually gather that information? So that is where the notion of optimality comes into picture. This is a problem statement. Okay? And this is, since we are working in 2D space, we have, there is a concept of convex polygon. The convexity we want only to prove certain nice properties, otherwise that is not required. And you have 5, remember these few things. You have Q, this is what I will be using. Q, if this is the room, then Q is this room. Okay? A point in Q is called small q. And then I think if Sujit is talking about this, Sujit also uses this kind of concept where we use something called uncertainty density. What is uncertainty here? Suppose there is some object here. Okay, before I start the search, I will not know whether there is an object or no, right? So that lack of information is uncertainty. If I do not know anything about that, the uncertainty is 1. When the uncertainty is 0, it means that if there is an object, that is, there is a target, I have successfully detected it. If there is no target, I know there is no target. So this, instead of information, we use lack of information to model the uncertainty density. Then these are locations of my robots. Okay. Actually, the robots are not on ground. Strictly speaking, these are actually the projection of the current location of UAV on space Q. So you have to deploy these N quadcopters or UAVs in Q in some optimal way to gather information. What is gathering information here? I take a snapshot, I do image processing, and then I detect the objects, right? So that is the information gathering. And these things typically do not happen in a deterministic way. That is what I will come to. So as I gather information, the uncertainty reduces. So I want to gather 100% information. That means I want to reduce uncertainty to 0 everywhere. This is a mathematical statement of the same problem. Okay, so in my PhD thesis, I did not use any sensor, realistic sensor. It was purely theoretical in nature. So when we send papers, we just say that cameras can be used. There are a lot of review questions about what is the kind of model that we use, whether that is acceptable. So in one of my students' PhD thesis, we try to address that problem. So this part is, it is mixed. It is both mixed of my thesis and my student's thesis. Okay, so quadcopters typically have front-facing cameras or oblique. Okay, or they can have the downward-facing cameras also. If you want to look for a large area, front-facing cameras will not be able to look below them. All right. So if you have the UAVs which have downward-facing cameras, they can look at a larger area and they can gather more information. So we use that model. Okay. And then we have defined something called search effectiveness. Search effectiveness is related to the target detection probability. Okay. So there are various search effectiveness that happens. So one is this one, this fellow, where whatever is under the camera, it is so clear that I have detected all the objects, targets that are within my field of view successfully. This kind of things are useful more in ground robots. Okay, UAVs which are flying high, it is less probable that you can detect all of them very clearly. Okay, so this is not what we use here, and this is what is. There is a continuous variation. Search effectiveness will assume for time being, okay, is maximum directly below the camera, and as you go away, so this is what we used for our convenience when I was doing my PhD. Okay, so the review comments and things like that, we realized that this has to be demonstrated. That is what I am doing in next few slides. Okay, and if I am correct, this is what Sujit used. Where, so I use a continuous space domain, and here actually instead of using a continuous space function of in a continuous space, you discretize the space, and you have a grids. The grid which is falling directly under the camera will have maximum uncertainty reduction. As you go away, it fades. Okay. So we will, in this work, we will use this particular effectiveness. Okay. We will demonstrate why that makes sense. Okay. So this is not our work. This is from literature. This is actually the central pixel This is as you go away from the central pixel. I will not explain all these things. The resolution of the image degrades as you go away from the central pixel. This is actually for a Nikon camera. Okay, obviously it has to be for a specific lens. I did not have the details there. This is from the literature. So this justifies our use of a sensor effectiveness function, which actually degrades as we go away from the center. This is from the perspective of optical resolution. Okay. So in modern day cameras, digital cameras, there are two layers. One layer is actually the optics. The second layer your sensor. There is something called quantum efficiency, okay, which talks about the effectiveness of the sensor. Noise reduction. There is noise, and once the image, light falls on the sensor, you have to amplify that. Okay. During that process, lot of things happen. Okay. So this efficiency also, you can see the central pixel shows that it is maximum. As you go away, the image resolution is bad, relatively bad. If you take it from sufficiently close, it may not make any difference. Okay. So that is a scenario from the literature. Then what we did is, if you want to get a PhD, a student cannot just use the literature, right? They have to do something. Okay. So we use some simple web camera, kept it on the top, and bottom, this is only showing the one-dimensional version of that. It's basically a rectangle. We kept these triangles are basically, we used few targets. We used triangle and we used Aroka markers. Okay. So the camera takes an image, and we added, instead of adding real noise on the floor ground, we added noise at the image level. Okay. Then what we did is the probability of detection. This is one representative picture where we show that there is a maximum detection probability in the center of the pixel, and as you go away from the center, the detection probability reduces. And this justifies the model that I used, or we used during my PhD. We used a sensor effectiveness model which is exponentially decaying in this fashion. Okay. So at the center it is maximum, as you go away it will reduce. We use this for a different purpose. Why R squared? Because I had to differentiate it and things like that. So from a theoretically to get nice results, we use this, but this experimentally kind of demonstrates that this function in fact can model the realistic situations. We did lot of experiments here. So as you increase the noise level, the K came down and alpha reduced. K coming down means this is the maximum efficiency. Reduced K means actually even at the center the effectiveness is not very high. Alpha increasing means it becomes flatter and flatter. Okay. So this is the model that we have used. I had used in my PhD work from a theoretical sense. So this part of work actually demonstrates why it makes sense. Please alert me. Okay. And see, basically what is happening here, let me talk about this. I will not explain this, instead of I'll tell you what is happening. You have a quadcopter here. Okay. First thing is you optimally somehow deploy them. Okay, that we will come to later. Once it is optimally deployed, it takes a snapshot and it does the image processing and does the target detection. Now what happens is uncertainty is reduced because information is gained. Okay. So what is uncertainty? If this is my search effectiveness, this was my initial uncertainty, say it is 1, I don't know anything. Okay. After first snapshot, what happens is, here uncertainty gets reduced by maximum amount because information gain sensor is more effective. Here there is no information gain, so uncertainty doesn't reduce. So uncertainty, if you consider uncertainty as a physical thing, you dig uncertainty, but not uniformly. You dig it more deeper at the center, and at the corners it will be like this. Okay. So what happens when you take a snapshot, you do image processing, you detect the targets, that is a real thing happening. But at the information level, I don't bother about all those things. What happens for me is, I gain information, so uncertainty reduces this way. Okay. Now based on this model, I have to find out how do I deploy my robots so that in one stretch the uncertainty is reduced to maximum extent. Okay. So that is what is this. I will not get into the math of this for lack of time. I will show you the simulations where you can appreciate it. This one I want to spend, I will, without saying this, look at this. What I am doing is, this is uncertainty reduction. What is phi is uncertainty, delta phi is reduction in uncertainty. It is always reduction. This uncertainty will not increase, it is always reduction. Okay. So this is reduction in uncertainty over entire cube. But because of Voronoi partition, it becomes each individual Voronoi cell, I need to worry about only uncertainty reduction within that. An integral over whole of the space is now divided into sum of integral under each Voronoi cell. This is what is distributed computation indirectly. That is because the system itself is distributed. I will not get into the detail of equation. Okay. So don't worry about all the complicated stuff. Finally, with lot of mathematical juggleries, we actually convert this problem. This is the gradient. This is the objective function, which is uncertainty reduction. You want to maximize that. This is the gradient of that with respect to position of the UAVs, and that is this, where this is an indirect centroid, not a direct centroid, of the Voronoi cell corresponding to robot I. Okay. Now, for optimality, the first order condition is the gradient should be 0. That means each robot, if it is located exactly as the centroid, then you have an optimal you maximize the reduction in uncertainty. Okay. So that is what this achieves. Remember, this is a multi-robotic problem. It's a multi-center object, optimization problem, objective function. But what I am seeing here is, you don't bother about what is happening to other, robots. You just be in your own Voronoi cell and try to move towards your own Voronoi, centroid of the Voronoi cell. That will optimize entire thing. So this is also indirectly, basically distributed computing. Okay. So this is what it means. Okay, spatially distributed in the sense that each robot will compute its own objective function, optimize its own objective function. It need not worry about others. Okay. So that is where the distributedness comes here. And this is the high level control law, not the low level control law, because we don't consider the dynamics of the UAVs. Okay. So this is the proportional control law, which is also called, from a control theory perspective, I see it as a proportional control law. But in this domain, it is called Lloyd's law because it's from a computation perspective. Okay. So these are the theorems which we will not go through. And I did not tell you what is sequential deploy and such. Very briefly I will tell you. I will not take more than 30 seconds for that. What you have to do is, no, I will explain when the simulation result comes. Okay. this is one thing which was very obvious to me. Your uncertainty is always monotonically decreasing function, right? So I thought it is obvious that it has to be, it should go to 0. Doesn't it look obvious? Something is monotonically decreasing, so every step it decreases, so you think it has to go to 0. So I told professor that I have proved it. He gave me a counter, example saying that that condition is not sufficient. Otherwise, this is a trivial thing. Even this proof is not trivial because our, first order logic doesn't work many times. Okay? So main things are, one is spatial distributedness. This is where it is connected to distributed control or distributed computation. My purpose is not computation, but finally you have to do computation. So the computation happens in a distributed way. Okay? And then I have to say this, from a control theory I have to say that this controller in fact indeed works. So that is what is this, and this finally is that at the end of the day, what is the implication of this? Implication of this is I will identify all the targets present in this thing given sufficient time. Okay, so let me not spend a lot of time here. Some of the students who are working, this is something which was very important contribution. The subtle difference between distributed and decentralized, many people will not know. Professor spent a lot of time in kind of convincing me this. This is a centralized controller. This is a decentralized controller, and this is a distributed controller. Okay, there is a lot of subtle but very important difference. So even when we were writing papers, some of the reviewers will not understand this difference. And what we finally used is something called a hybrid controller. For my students' work, not me. I did not bother about all of things. My simulation was centralized. Okay. So this is optimal deployment. These are all point masses, no dynamics involved, only kinematic level simulations. And I do not have, like guidance, I do not have a problem like turning radius constraint or anything. I have quadcopter, they can move anywhere. Okay. So this is initial location. These are all Voronoi partitions. These are all Voronoi cell. This is the current centroid of the Voronoi cell. So each robot will try to move towards its centroid. Okay, you can see that. Okay, it will keep moving, and at the end you can see that now they are reasonably equally distributed. So all of the red dots, red discs which represent the robot are in their respected centroid, and each robot is computing only within its Voronoi cell. But Voronoi cell itself is a function of neighboring robots. So that is where the coupling goes. Okay. So what basically happens is they optimally get deployed. They take a snapshot. Uncertainty reduces. Now situation has changed. Now wherever I am is no more optimal. So I look for next optimal deployment. So sequentially optimally deploy, do search, deploy again, do search again. Okay. So this is my original uncertainty. After first search, this is what is my uncertainty. I have reduced. So remember one thing, this is not an animation. The scale is different. Okay. These are just snapshots and different time instances. So uncertainty reduces. You have that inverse this thing, and then it further reduces. You can observe that the resource 0.2 there, now it is 0.25. So basically at the end maximum uncertainty is 0.05. So this is theoretically showing that uncertainty reduces. I don't do any image processing here, I don't do actual things, this is only at the abstract level. Okay. So let me skip this thing, this is not important. Okay. So So during my postdoc, I applied it for another problem called complete coverage. This is also coverage problem. This coverage problem is called sensor coverage. So the sensor range is long, very big. Whereas if you want to do a landmine detection or vacuum cleaning of a room, your sensor footprint is of the size of the robot. So if you want to clean this room, you cannot stand in one place and say, I have cleaned the entire room, right? You have to physically go there. Right now, if you have multiple robots, there are a lot of problems. If you have multiple robots, then the task allocation becomes an issue. And each time robots have to communicate, what is the area I have covered, so that somebody else doesn't cover that. Okay. So that problem of task allocation and optimality, both can be addressed by Voronoi partition. If this is the initial location of the robots, they are physical robots, they are actually this robot. Okay. They are called co-robots, and this is simulation within some software called Vibots, which actually does a realistic simulation. Like ROS, you have gazebo kind of thing. Okay. So this is one Voronoi cell. This is Voronoi cell of this robot. This is Voronoi cell of this robot. This is Voronoi cell of this robot. And each one of them don't bother about what is happening in the neighborhood. They cover that area completely. This is a very simple thing, but it solves the problem very elegantly. Now suppose one of the robot dies. In any multi-robotic system, one important aspect is you want to have robustness to failure of some of the robots, right? So in my previous thing, if one UAV doesn't work, nothing happens, you will still successfully, reduce the uncertainty. Here what happens is you have to do something extra. So these remaining things, I will repartition based again on Voronoi partition. So this part of it is taken by this part of it is taken by this part of it is taken by this. Okay. So you have a lot of variation. This is actually based on my postdoc work, but I graduated a PhD student from NITK who worked on generalization of this using generalized Voronoi partitions, and so I am not showing those kind of things. So the reason I am presenting here is two things. So I got introduced to multi-robotic systems, though from UAV perspective here in this GCD cell with Professor Ghosh, and I started using Voronoi partition here. So in a completely different problem, I could use a similar technique and solve the problem. Okay, this one I will not want to talk about. So other problems, this is what I told you, and this was my master's work with Professor Ghoshal. I don't want to talk about that at this point of time because we don't have time. And this is one of my PhD students' work. This is what I talked in Professor Ghoshal's retirement symposium, where use the concept of distributed control for a single manipulator. In a typically distributed control, you talk about in a multiple robots, right? So you have a single robot, each joint link pair we considered as a agent and applied that. And this is based on the Voronoi partition based coverage I told you. This is based from the thesis of one of my students. Okay. And these are, okay, this is another very interesting thing. So I will not show you this again. This is computation of Voronoi partition in a distributed way. Okay. And these are my credit to my collaborators. Started my career with Professor Ghoshal, and the major chunk of my training happened here in aerospace with Professor Ghosh, and this is my postdoc guide. And these were students during my postdoc time. These are my students at various, few students who have graduated. So these are PhD students, these are masters, and masters by research. These are masters, these are BTech students. And thank you. And I hope this is an interesting story. This is at NITK. As soon as I finished my PhD, I went back there, and I had organized program on multi-agent systems, because that is where I just finished. And he was my colleague. He's my colleague in NITK. Dr. Vasudeva. I don't know why. He sent this picture to me today when I was a teacher. Okay, and Professor Ghosh was the guest there, and he inaugurated the. Thank you. I think I don't have time for that.